I apologize for not having a nice Australian accent, but you get what you get.
I realize you're going to call me an American mathematician.
This is all joint work with David Buter at Temple University and Saul Schleimer at Warwick University. And I wanted to say too, this is a little bit, quantum topology and hyperbolic geometry is the theme of the conference. We're going to be a little bit heavier on the hyperbolic geometry side, but hopefully there will be things here that would be applicable for others as well. Okay, so let me start out this talk with some background that probably all of you know. This is a talk about Dehn filling, or drilling, depending on how we're looking at it. So Dehn filling, it's this topological notion that has been around pretty much forever. You take a three-manifold with a torus boundary, and you take a slope S on the boundary of M. And then you are going to attach to this a solid torus so that your slope S bounds a disk, and we're going to denote this by the M of S. Okay, so that's your resulting three-manifold. And it's due to Wallace and Lickrish in the early 1960s that every closed orientable three-manifold is obtained by Dehn filling a link in the three-sphere. So Dehn filling is an important way of studying three-manifold topology. Okay, but this is a geometry talk, so let's skip ahead a few years. It was Thurston who really made Dehn filling geometric, and this came up in the last talk. He talked about hyperbolic Dehn filling. So the setup again is that we have a three-manifold M with boundary that is a torus, and the interior of the manifold in this case will admit a complete hyperbolic structure. So what that means is the boundary of M is this torus. It's not part of the hyperbolic manifold anymore. If you lift to the universal cover, hyperbolic three space, then your torus is going to be lift to a collection of points at infinity. So you can take the point at infinity, for example, in the upper half space model. So here's our manifold. The interior of M is the quotient of H3 with a discrete group of isometries. The boundary, sorry, I should say a tubular neighborhood so the boundary is going to lift to the boundary at infinity, but the boundary to tubular neighborhood of the torus is going to be lifting to some sort of a horosphere. And if you look at the intersection of that horosphere with the manifold, then a fundamental domain for that is going to give the fundamental domain of a torus. And you get a complete structure if and only if on this horosphere you get a complete Euclidean structure on your torus. So you'll have some sort of a tiling of your horosphere by parallelograms that fills out the plane, this particular horosphere. Okay, so this is a if and only if condition for a complete structure. But if you deform this complete structure, then you will get incomplete structures, and you will get affine structures on your torus. So this is a picture that I took from Thurston's notes, 1979 notes. So for example, if your hyperbolic manifold is built of ideal tetrahedra, for example, you can just bump the hyperbolic structures on the tetrahedra just a bit. The effects on the Euclidean structure on the torus is that you get something. These nice straight parallelograms are no longer parallelograms. They're just some sort of generic quadrilateral. And then when you look at the developing map, they're going to spiral around on your horosphere, and they are going to miss a point somewhere on the horosphere. Okay. This is still a hyperbolic structure. It's not a complete hyperbolic structure. You can take the completion. So if you take the completion on this particular horosphere that we're looking at on the developing map, you've got to add a single point on this horosphere. So and now you've got a stack of horospheres going up to infinity. On each one of them, you want to add a single point. The fundamental group of the manifold is going to be acting on this stack, and the point, this pink point that I've drawn here, is going to be identified to other points. So if the point is identified to a dense set on this stack of horospheres, then when you take the completion, topologically what you're going to do is you're crushing a dense set of points on the boundary to a single point. And this ends up not being a manifold. So this is case one in the completion. But there is something nice that could happen, which is that the translate of this pink point vertically ends up being a discrete set of points. And in this case, when you take the completion, then you are attaching a closed geodesic to your manifold. And this is homeomorphic to the Dehn filling. Okay? So Dehn filling, in the geometric sense, is just obtained by deforming a complete hyperbolic structure. And you can always deform a complete hyperbolic structure in a neighborhood of that complete structure. And so you'll get infinitely many Dehn fillings coming out of this. In fact, all but finitely many. And so this is Thurston's hyperbolic Dehn surgery theorem. Okay, so he showed that if you have a 3-manifold with torus boundary whose interior meets a complete hyperbolic structure, then all but finitely many slopes, for all but finitely many slopes, the Dehn filling admits a complete hyperbolic structure, and the idea is just deform as shown. Okay, so I should say too, the geometry here, when you attach a closed geodesic and you end up with something homeomorphic to Dehn filling, you don't always get a complete structure on that. More generally, you'll get a cone manifold. So that's what I wanted to describe next. Okay, so we attach this curve that I've drawn in red. This is, if you take the completion of this deformed hyperbolic structure, you're attaching a geodesic. The geodesic has a tube around it. And if you take a disk, like a cross-sectional disk around the tube, it could happen that your disk is nice and flat and gives you a hyperbolic disk. This is called angle alpha equals 2 pi. In this particular case, you do get a complete metric on the Dehn filling. More generally, you're going to have some sort of a cone manifold structure. So this is where you take a cross-sectional disk of the tube that you've just added, and it's going to be bent. It's going to have the metric of a cone. So there's going to be some angle around this this geodesic that you just added that's between 0 and 2 pi. Okay, and so this is a cone manifold. So it's still homeomorphic to a Dehn filling, but it is isometric to a manifold with a singular structure. And if you let your angle approach 0, then your cone gets steeper and steeper and steeper, and in fact you end up with your cusp structure that you started with. So this would be the complete cusp structure. Okay, so that's the geometry that's going on underneath the Dehn filling. And these cone manifolds have been very useful for studying the geometry. Let's see, so what's next? So I should say too, Thurston's hyperbolic Dehn surgery theorem is not an effective theorem. It just says that all but finitely many slopes, you get a hyperbolic structure. It doesn't tell you which slopes. So this was investigated several years later by Hodgson and Kirchhoff. So they have, using cone manifolds and these deformation through cone structures, they came up with effective hyperbolic Dehn surgery theorem, which says the following. So again, the setup, you've got 3-manifold with torus boundary, the interior admits a complete hyperbolic structure, and you have a slope with a long length. And I'm going to say something about this notation in a second. Then the result is the Dehn filling must be hyperbolic if the slope is this long, this universal constant. And not only that, you can deform from this complete cusp structure over there on your, what is that? That's your right, to the complete filled structure over on your left through these cone manifolds. So you can go all the way down by a sequence of cone deformations, is what they're called. So the angle increases from 0 to 2 pi. Okay, and this L is the normalized length of a slope. In this horospherical torus, the slope S will, which I've drawn here, right? So S is going to inherit some sort of a length on a horosphere in this Euclidean structure. And you take the length and you divide out by the area of the horospherical torus, square root of that, and that's going to give you the normalized length. This is independent of the choice of horosphere that you choose. But the key point is there's this universal constant that works for any manifold and will give you this hyperbolic geometry. So this is an example of an effective theorem. Oh, sorry, corollary. So any manifold, because you have this universal 7.515 length, any manifold as above has at most 60 non-hyperbolic Dehn fillings. All right, so this is an effective theorem. What's that?
I think that column is the theorem of constant.
Yes, this is a Hodgson and Kirchhoff used this, plus Agel had some results that bounded. So given the length of 7.515, Agel says that there are this many slopes can be excluded. So yes, this is all in Hodgson and Kirchhoff's paper. I may be being overly generous to Ian Agel. It was his idea to reduce to this finite number of slopes. But yeah, so any manifold as above has at most 60 non-hyperbolic Dehn fillings. So now, this is a really great result, because now if somebody hands me a manifold, you give me your favorite manifold, I can come back to you and say, well, I know that all but 60 of the Dehn fillings on this manifold are hyperbolic, and if you want me to tell you about the remaining 60, then I can use, that's a finite number of things. I can use different techniques, computer, or some ad hoc methods, and say something about these remaining cases. Okay, so it's much, much more applicable to examples than the original theorem. Yes?
But 60 is an overkill, right? So what's the
for
dream?
hyperbolic, there's a sixth theorem due to Agel and Lackenby that you can reduce down to, how many? 12, I think, from the sixth theorem?
Right.
That's right. What you don't get out of the sixth theorem is this deformation of geometry. So the deformation is important for my talk. If you're just interested in hyperbolic geometry,
But
then 12.
even with deformation, do you really expect 60 or do you expect like 40?
Oh.
I mean,
The analysis doesn't really work. The analysis is hard. But I don't know. Yeah. I mean, conjecturally, any time the Dehn filling is hyperbolic, there's actually an open conjecture that you can deform three-cone manifolds all the way through. But that has not been proved, and that seems to be quite hard. So yeah, so you would expect 12 still.
For hyperbolic paths, isn't the figure 8 not conjectured to have the most?
Yes, that is true. For hyperbolic knots, the figure 8 notch is conjectured to have the most at 10? 10?
Yeah.
I am speaking about, one boundary component. Yeah. If you allow, there are versions where you allow multiple boundary components. In that case, you exclude finitely many slopes from each component. And this is true. So pretty much everything I'm going to say has one boundary component, but it also extends. You just have to be careful with multiple boundary components. Okay, other questions? All right, so this idea of cone deformation is extremely useful because you know geometry here. You can follow the geometry all the way along the deformation, and then you can say something about geometry over here, in theory. Okay, so Hodgson and Kirchhoff, in their paper, they controlled some geometry between. There are various geometric things that we're interested in controlling when we deform from a complete structure on one hand to a complete structure on the other hand. And it would be useful. So Thurston's hyperbolic Dehn surgery theorem says that one is a geometric limit of others, but it's ineffective. And so in order to apply this, we need to be able to say things about particular manifolds. So the first result along these lines is due to geometry change. Okay, it's due to Brock and Bromberg, I should say. But in their setup, so I've been talking all about starting with a manifold M that is unfilled and taking a long slope on M. And then deforming by some sort of a cone deformation to a complete Dehn-filled manifold with this special geodesic in it. So these are supposed to be different colors. Do they look different to you? They don't look very different up there, do they? Anyway, well, oops. Okay. So there's your new geodesic when you're done, and this new geodesic is going to have some sort of a length. This is the completion. This is the guy that you put in when you completed the deformed structure. And it's got some sort of a length. But you can also go the other way around. So this deformation, once you have it, it goes backwards. Or conversely, if you have a short enough geodesic, then you can prove, this is what was done by Bromberg and by Bromberg, that you can go the other way around. So given a filled manifold, then with a short enough geodesic, then you can deform through cone manifolds to a drilled manifold. So we have the drilled manifold is the cusped, and the filled manifold is the completed. All right, so Bromberg drilling theorem. They proved, this is in the early 2000s, they proved that for any j greater than 1 and any epsilon greater than 0, there exists some L, length bound, such that if you have a hyperbolic 3-manifold with a simple closed curve gamma of length less than L, then when you drill this, the identity map gives you a J by Lipschitz diffeomorphism on the complement of the epsilon tubes about this gamma. So in other words, let me say this slightly differently. They start with a filled manifold. Oh, my pen just died. They start with a filled manifold, and they do, okay, there it's back. They start with a filled manifold, and they find that if the length is short enough, then there's a sequence of cone deformations that goes from the filled manifold back to the cusped manifold. And not only that, all along the way, you get geometry control. So the identity map is a J by Lipschitz diffeomorphism, meaning that the metric is changing in very controlled ways by J by Lipschitz.
So gamma is not just simple closed curve, right? It should be somehow topologically non-trivial, or?
Gamma should be a simple closed geodesic.
Okay.
Yeah, so gamma is a geodesic. Okay. All right, so this has been a very important theorem. So lots of applications and advantages to this. It was initially proved by Bromberg and then by Bromberg to prove instances of the density conjecture for Kleinian groups. It's been used to show that deformation spaces of Kleinian groups are not locally connected by Bromberg and Aaron Magid. I've used it in the past in a few ways. So when I'm looking for examples of geometric limits, work with Tuto, or to show existence of manifolds with certain geometry and work with Cooper and Futer, then you can use this theorem to show that there exist manifolds with certain geometry because I know that if L is short enough, then blah, 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 blah. Disadvantage, though, is, again, this is ineffective. So what is L? It doesn't come out of the J or the epsilon. So if somebody hands me a manifold and says, okay, does this work for the theorem, I don't know. Okay, so you cannot apply it to fixed manifolds or examples. You can't go into algorithms or computational problems. All right. So anyway, with Dave and Saul, when we started working on, we were looking at other problems, and we realized that it would be really, really useful to have an effective version of this drilling theorem. And and eventually, after we kept bumping into this several times, we decided, well, how hard can it be? Let's just go and prove it. And many, many years later, and several tens of pages, we now have an effective version of this. Okay, so this is our main theorem. We can state this, the statement is a little bit complicated, and I'll say a little bit of what goes into it, but the key point is there is an effective bound on your slope length, L. So fix an epsilon between 0 and log 3. Let M be a finite volume hyperbolic manifold with a geodesic link inside of it. So here we do allow links, but you can think simple closed curve or simple closed geodesic. And suppose that in the hyperbolic metric on the filled manifold, this closed curve has length bounded by this some function, or alternately in the hyperbolic metric on the drilled manifold, you could also take a normalized length of your slope to be big, where this is quantified. So then in that case, there will be a J by Lipschitz inclusion from the thick part of M into a thick part of N, and vice versa, where J now is a function of your L and your epsilon. You can redo this theorem to take this for any J. You just have to change the hypothesis fees a bit. And in the case that you were looking at large meridian length, you also get bounds on your the curve when you're done. Okay, so that's the statement. Just some quick notation. This m greater than or equal to epsilon denotes the epsilon thick part of the manifold. This consists of all the points which have an embedded isometric ball of radius epsilon over 2 centered at x. Okay, and I'll say a little bit more about that later.
In your theorem, is there an or?
Yes, that is an or. So you can either take the filled manifold and go and drill, or you can take the drilled manifold and fill. Either way works. It goes two ways. It's a two-way theorem. Okay. All right. So I'm actually not going to spend time on talking about the proof of this. It does follow through a lot of the Hodgson-Kirchhoff cone deformations, the Brock-Bromberg. Where do these awful functions come from? Well, you've got to find areas of tubes about thin parts. You've got to find distances between thin parts, and then you've got to bound things using some analysis. And keeping hold of the effective constants, it just gets kind of uglier as the page count increases. But it happened. So what I want to talk about instead, so let me see how I'm doing on time. Oh, sorry, fine. Are a couple of applications of this. So we have two somewhat immediate applications. Number one is we get reductions to the cosmetic surgery conjecture. This is a conjecture of Gordon from 1991. Or number two, we can also determine there's a conjecture about optimal Margulis constants from 1967 that we can also say something about. So this is where we're going to go from here. Okay, so any questions so far? All right, great. All right, so now I'm going to start talk number 2 on the cosmetic surgery conjecture. Okay, so let me tell you what the cosmetic surgery conjecture is about. If you have a 3-manifold with torus boundary and 2 distinct slopes on that boundary, then we say that P1, P2 is a cosmetic surgery pair if the Dehn-filled manifolds are homomorphic. And we are only going to be looking, for purposes of my talk, we're only going to be looking at purely cosmetic pairs. And this is what you get if this homomorphism is orientation preserving. Okay, so for example, if you take M to be the unknot sitting in S3, so there it is. This is homomorphic to a solid torus. And if you fill along the slope 5/2, then you are going to get a lens space called L5/2. If you fill along the slope 5/7, then you are going to get a lens space, which is also 5/2. So this is a purely cosmetic surgery pair in this particular example. Okay. Okay, so Gordon conjectured in 1991 that if M is a 3-manifold with a torus boundary and it's not homeomorphic to the solid torus, then essentially there are no purely cosmetic pairs. If you have a purely cosmetic pair, then the 2 slopes have to agree. So this was the conjecture. Okay, there's an old theorem. This is, we say it's a folklore theorem, but it's written down in a paper by Bleiler, Hodgson, and Weeks, that if you have a cusp hyperbolic 3-manifold and you have 2 slopes that are sufficiently long, if these happen to be a purely cosmetic pair, meaning the Dehn-filled manifolds are homomorphic by an orientation-preserving homomorphism, then the 2 slopes must agree. The way this goes is basically it's Thurston's hyperbolic Dehn surgery theorem. If they're sufficiently long, then the manifolds will be sufficiently close, or you get the change in geometry is going to be sufficiently small, and then Mostow rigidity will tell you that these had to have been the same slopes on the original guy. Okay. All right, but again, this is ineffective because there's no quantified number. What does sufficiently long mean? And so this is something that we are able to quantify. So here is our theorem. So let M be a cusped hyperbolic 3-manifold with slopes S1 and S2. And let's suppose that the normalized lengths are both larger than the maximum of these two quantities. So one of them is a fixed constant, 10.1. The other one is the square root of 2 pi over the systole. I didn't say what the systole is. Here's the systole. The systole is just the length of the shortest closed geodesic inside of M. Okay. So then the result is that if these are a purely cosmetic pair, meaning the Dehn-filled manifolds are homeomorphic by an orientation-preserving homeomorphism, then S1 and S2 have to agree. Okay. So in particular, the maximum is going to be 10.1 if it happens that your systole is at least 0.1428. And then your length of your, normalized length of your slopes is at least 10.1 in this particular case. And this is, for small manifolds, the systole is usually pretty big. So for example, if you look at the SNAP-P census, then the systoles in there are, almost all of them are bigger than 0.1428. Okay, so there has been a lot of work. I should probably say more on it, but there's been a lot of work on this cosmetic surgery conjecture, especially in like the Haggard floor realm. There's recent work of Ni and Wu that additionally will reduce the search. So this is a corollary from our paper, but it just says that if you've got a hyperbolic knot with meridian and longitude M and lambda, or mu and lambda, and a pair of a purely cosmetic pair of slopes R and R prime. So in other words, if you have a knot that does not satisfy the cosmetic surgery conjecture, then you know that these two things have to hold. So number one, the length of the first slope has to be less than this maximum. This comes from our theorem that I just showed you. And number two, you also, this comes from Ni and Wu, you get some control on the second slope as well. So R prime is just negative R, is what this is saying. R prime is negative R. And furthermore, you have conditions, so P divides Q squared plus 1. Okay. So now this information really gives some pretty serious restrictions on slopes, possible counterexamples to the cosmetic surgery conjecture. So then, right, so for a knot in S3, all you have to do, you need to find the systole, which you can do using SNAP-P. Usually it's pretty large, and then you need to check a finite number of pairs, R and negative R, to see if you get a counterexample to the cosmetic surgery conjecture using this theorem. And so we did this. Here it's a computational result. Is the cosmetic surgery conjecture is true for all knots up to 12 crossings. So by making this these lengths effective, then we're able to turn this into a computational problem and run it through and get some results. So 12 down, just a few more to go, and then the conjecture will be proven. Right? Okay, so in fact, I've been talking about, so if you hand me a manifold, maybe it's not, if it's not in S3, then I can run it through this thing. I can check a finite number of R and negative R and tell you whether or not it satisfies the cosmetic surgery conjecture. In fact, if you give me any hyperbolic manifold, you can use this work to reduce the cosmetic surgery conjecture to a finite search in it for any manifold. And so let me say a little bit about how that works. I think I'm speaking too fast, but nobody will object if we have a long tea break, right? Okay, here we go. So, all right, so how does this work? So let's take curly S here to be all slopes whose normalized length is less than the maximum of 10.1 and this square root of 2 pi over the systole plus 58. Okay, so you handed me M, and then I can compute its systole, and so I can find a finite number of slopes whose normalized length is less than this bound. If it happens that we have a counterexample to the cosmetic surgery conjecture, then it follows that one of the two slopes has to be in this curly S. So let's say, without lots of generality, let's say the S1 is in there. Okay? All right, so the next thing that goes into this is these two manifolds, the Dehn fillings are homeomorphic. So look at all the volumes of the Dehn-filled manifolds for slopes S inside of curly S, and call that V. So there's a finite number of things in curly S, so we can take a finite number of volumes. We know by Jorgensen and Thurston that their volumes are all bounded by the volume of the original unfilled manifold. And then there's a theorem that I have with Dave Feuder and Epi Kalpajani that gives you bounds on the volume. So if the volume of M of S2 is less than or equal to this constant V, then it follows that the length of this slope S2 has to be bounded by 2 pi times a computable value, right? 2 pi times, this is a 1 minus V over the volume of M to the 2/3 power, and then you take the 1 over the square root of all of this. All right, so it's a formula that's computable. And so this number over here is going to give me a bound on slope lengths for S. And so we're going to define S prime to consist of all slopes R whose length is bounded above by this value coming out of the volume bound theorem. And it follows that if S1 lies in curly S and the two volumes of S1 and S2 agree are less than or equal to V, then S2 is in S prime. So therefore, if S1 comma S2 is purely cosmetic, then it means that S1 and S2 lies in this finite set consisting of curly S and curly S prime. Okay? All right, so unfortunately we cannot, at this point, go from here to a proof of the cosmetic surgery conjecture, but we can do it for any manifold that you give me, we can prove it. But there are still infinitely many manifolds to go. Okay. Any questions so far on this? Oh, sorry, I should say too, there's a lot of related work. So the Hagard-Floor people, I mentioned me and who. Jonathan Hanselman has also been looking at cosmetic surgery conjecture for knots up to some number of crossings. In the hyperbolic setting, Bo-Guang Jian has some work where he's been looking at multiple cusps and extensions to orientation reversing as well. So this is all work that's also been done.
Why can't you just run this check on the snappy census manifold?
Yeah, so you could run this check on the snappy census manifold. It would take a long time. Yeah. But yes, but it could be done, in theory. All right, so now I want to talk about Margulis constants. So this is talk number 3. Okay? Margulis constant. So this is going back to hyperbolic geometry again. I talked about the epsilon thick part of a manifold earlier. That's the part of the manifold where you can stick in an embedded hyperbolic ball without it bumping into itself. So the epsilon thin part is the complement. This is M minus the epsilon thick part. And equivalently, so if you cannot embed a hyperbolic ball, that means when you try and put the ball in there, it bumps into itself. You get this non-trivial something. That means it picks up an essential loop. So there's some sort of an essential, possibly pointed geodesic sigma that runs through your point X, and it has loop strictly less than epsilon if you were in the thin part. Okay. So for example, if you have a cusped hyperbolic 3 manifold and you take any point on a horosphere, say X, it's going to have some height h, say, there's going to be a translation, follow the meridian or whatever that is, some to give you a point that's glued to x, and this is going to have some Euclidean length in that particular horosphere. Its hyperbolic length is going to be this Euclidean length divided by h, and then the distance between these 2 points is actually going to be smaller than that. So you get this upper bound, you let h go to infinity, let h go to infinity, and this length is going to 0. You can make the length as small as you want. So if M has a cusp, then for any epsilon, the thin part is always going to contain a Horobal neighborhood of that cusp. In 1967, in a paper of Kasdan and Margulis, it was shown that there is a universal number, epsilon 3, such that if delta is less than this value and M is hyperbolic, then the thin part is a disjoint union of cusps and neighborhoods about tubes. So the only thing that can happen is you have cusps, like in this example, or you can have very, very short geodesics and tubes about those, and those are your pieces, your thin parts. Okay. All right, so following this, we say that epsilon is a Margulis number for a fixed manifold M if the thin part is a disjoint union of cusps and tubes. And notice that so we can define an optimal Margulis number to be the supremum of all such epsilon for M. You have to observe in this case that if delta is less than epsilon, then M, the delta thin part is going to be contained in the epsilon thin part, right? So you would have things like your epsilon tube would maybe consist of a Horobal, but your delta tube would be a Horobal even higher up. So you get containment. So the optimal Margulis number, then you just take the supremum. So this is the maximum epsilon you can take and still get cusps and tubes in the thin part. All right, so this universal number that Margulis said that it exists, we're going to call mu3 now. This, I guess epsilon 3 is some universal number. mu3 is the optimal one. We're going to call it V3D. Margulis constant is going to be the infimum over all hyperbolic manifolds of the optimal Margulis number for that manifold. And it is an open question as to what this value is. So it's known, it exists, it's out there, but we don't know what it is. Okay, so open problem is to find the optimal Margulis constant. There are several known results along these lines. Rob Meyerhoff in 1987 showed that it is at least 0.104, and this is still the state of the art from 1987. The Margulis constant is at least 0.104. In terms of an upper bound, the Weeks manifold has Margulis number 0.775. So you know that the infimum of all of them has to be less than that. This is done by a computation by Jarmola. I don't know if it's written down somewhere, but it's known to people who know these things. Kohler and Shalin in 2012 showed that if you have some conditions on the first homology group, then your Margulis number has to be at least 0.292. So if the dimension of the first homology group, the rational homology is at least 1, your Margulis number is 0.292, and this includes every manifold that's not closed. So if you have a cusp, or if you are infinite volume, you have Margulis number at least 0.292. And then building on this work, in 2003, Peter Shalin showed that if your volume is at least 52.8, then the Margulis number is at least 0.29. And this is a nice effective theorem, but unfortunately it leaves infinitely many manifolds behind. So there are
excludes, not includes, right? You write includes infinitely many manifolds.
So what I meant by this is, now if I'm going to try to find the optimal, if I'm going to try to prove the Margulis number is at least 0.29, then I've got to check it on a set that includes infinitely many manifolds. So the manifolds that, yes, manifolds without Margulis number bounded by 0.29, they include infinitely many manifolds. So because of this volume bound that's effective, you know that there are only finitely many parent manifolds that will give you those manifolds, but all of their Dehn fillings are possibilities. So that's a lot of things to check. Peter Shalin in 2011 actually did show that if the Margulis number is at least 0.29, then, or sorry, the Margulis number is at least 0.29 for all but finitely many hyperbolic 3 manifolds. But the way that he showed this was by an algebraic limit argument, and it is not effective, and it cannot be made effective using those particular techniques. Okay, so that is where we are now. Okay, so what do we add to this? So it comes out of our cone deformation techniques that if you have a hyperbolic 3 manifold whose Margulis number is less than 0.29, then the length of the shortest geodesic inside that manifold is at least something very small, but is at least some effective bound. So 2.73 times 10 to the minus 8 is the lower bound on the systole length for this particular manifold. Okay, so then we can put these things together. If the Margulis number is less than 0.29, then it follows that M is a closed manifold. This is by the Kohler-Shalin result. The volume is less than 52.8 by item number 4 is still there. And the systole is at least 2.73 times 10 to the negative 8 by this result on this effective theorem on the Dehn filling. Okay, so this now is effective. There are only finitely many manifolds that satisfy all these 3 things. Okay, so how does it go? And there are algorithms to find these. So for example, there's a paper of Kobayashi and Rink that explains them. So how would it go? You find there are only finitely many parents with volume less than or equal to 52.8. And of those, there are only finitely many Dehn fillings that give you something whose systole is at least 2.73 times 10 to the negative 8. And then you list all of these manifolds and you run through them and you check to see whether or not the Margulis number is less than 0.29. And these will help you to find a better bound on the Margulis number in theory. Okay, so why is effective though in scare quotes? Well, it's because they're still, this is a huge, pretty much, it's kind of an impossibly large number of manifolds to deal with at this point. And so we have not dealt with it yet.
Roughly how many?
No idea. I don't even know how many Dehn filling parents there are, honestly. But this 2.73 times 10 to the negative 8, those are pretty high Dehn. That's pretty high slope lengths that are giving you Dehn
How big
fillings.
is the tower of exponentials?
I don't know.
But you can list links that are possible parents with that bound in the volume.
Yes, one can
And
list
volume
possible
52
links. Yeah.
lists 17, 18 crossing links. So you're on the billion
Yeah.
there.
Yeah. It's pretty big. Yeah. Yeah. So. Right, I haven't looked into the numbers carefully, but yeah, I mean, if Stavros' intuition, 17, 18 crossing links, if we just look at 17, 18 crossing knots, there are millions and millions of them. If we allow links, then there are even more. It's a lot of work. Maybe we can get somebody started working on it, and you can prove that maybe 0.29 is a better Margulis number now. Anyway, that is all that I have to say. That's the end of my talk. Thank you.
Any question?
So what's the situation for the Margulis constant in higher dimensions?
The Margulis constant in higher dimension? Oh, yeah. We can't say anything about that. I don't know. Yeah, none of this applies. This is all very heavily three-dimensional. Yeah, three-dimensional. All the techniques.
Dehn surgery is a very three-dimensional phenomenon.
That's right. All of this deformation doesn't exist in higher
I was
dimensions.
just asking if there's such an array of like this in dimension 4.
Yeah, that's a good question. I don't know.
I don't know if that's
This teeny tiny systole, right? You're taking 1 over 100 million or something, right? How is that a very high Dehn surgery to get that? What's the intuition? How do you get these teeny tiny little bitches?
How do you get the teeny tiny little? Yeah, it's a high Dehn surgery. Let me see if I can scroll up. So this meridian length will give you about that curve length. This is kind of huge. So epsilon is probably pretty small. You have to take 1 over epsilon to the 5th and multiply it by 2 pi times 6,771 times cosh of, this is, well, that may be not very big. But then when you're all done, out 11. Yeah, they're pretty big slopes. They're pretty big slopes.
I think your work can be generalized to any.
It can be generalized to to n-cust manifolds. Yes, it can. Yeah, the Dehn filling cares a little bit. You have to keep track of sums of lengths of short curves and sums of normalized. Well, 1 over the sum of the normalized length is what you need. But yes, it can be generalized.
More questions? Well, so we need to thank Jessica again.
Let me